Okay, so let's start with the review. Professor creates the Venn diagram below to describe the proportion of students who take chemistry and Spanish at the University of California, Irvine, where A, students take chemistry. So this one is chemistry, and this one is Spanish. Okay, find the value that this means or when you see the union there, so A or B. So the quick and easy way is just to add these three numbers. So that would be 0.6, so I know it's one of those. The other way is to take chemistry, which would be 0.2 plus 0.1, which is 0.3, plus Spanish, which is 0.4 together, minus the overlap, which is 0.1, and you get 0.6. Take either Spanish or both. That is exactly what we mean when we say or. We actually mean or both. Definitely does not mean and. So the union is or. The intersection is and. Toss a penny and observe whether it lands heads up or tails up. Suppose a penny is fair, and meaning the probability of heads is 1/2. This means that every occurrence of head must be balanced by a tail. Well, certainly that's not always true, right? There's random chance of this. If I flip 10 coins, it would be almost impossible to obtain. No, that definitely could happen, so that's not it. D is regardless of the number of flips, half will be heads. That's definitely not true. So certainly most of those are false. This is the long-term running frequency there, the long-run frequency. So as I do more and more flips, many trials, it will get closer and closer to the 1/2 probability. That's what the long-term frequency will be. To be a valid probability model here, so we've got all these M&Ms. They have just 6 different colors. We know that this has to add up to 100%, which is 1 essentially. So if you add those up, that's 0.8. So this one must be 0.2. Ignoring twins and multiple births, assume that babies born at hospital are independent random events, and so that a boy or girl are equally likely. What is probably the next 5 babies are girls? So that would be 1/2. These are independent, so we're just going to multiply 1/2 times 1/2 times 1/2 times 1/2 times 1/2, whatever that is. I think that is, if you use your calculator, 4 is E. Should clinical trials on issues such as heart attacks can affect both sexes use subjects of just one sex? The responses are in the table below. Suppose you choose one of these people at random. What is the probability the person says yes, given that she is a woman? So women, so we're only looking at these folks. So if you add up 46 plus 185, you get 231. So out of those 231, that's the given. What's the probability of yes? So that would just be, yes would be 46 out of 231, which I believe when you divide that is very close to 0.2. No, so how many folks said no? So that would be 105 plus 185. If you add those columns, you get 290. If you add the column there, and then female we just added is 231, so you would add 290 plus 231 minus the overlap. I think you counted 185 twice there, so that's my numerator. We know there's a total of 370 people, so that's my denominator, and that should work there. Select. Oh, by the way, the answer for 6 is D, I believe, when you work that out. Select a random integer from -100 to 100, which of the following pairs are mutually exclusive. So mutually exclusive events cannot happen at the same time. I think you can be odd at a number that is 5. Those can be the same. Numbers even, greater than 10, like 12 is both. Less than 5, numbers negative. Yeah, that definitely can happen. Number is positive, number is odd, so the only one that can't happen. Number can't be above 50 and below 20 and be the same number. That's impossible, which means it's mutually exclusive. If you buy one ticket in the provincial lottery, the probability you win a prize is 0.11. Given the nature, what is probably, so it's independent, you buy one for 5 months, that you will win at least one prize. Well, that's very difficult to find. I need to find the complement of that event. So if the chance of winning is 0.11, the chance of losing would be, if I subtract from one, I think 0.89. So if I do that for 5 weeks, I'm going to get some number here. And whatever that number is, it's going to be 1 minus that number would be my answer here. And when you do that, the answer is C, because that's the complement. Complement of winning at least one prize is not winning any prizes, and that's actually much easier to calculate than the probability of winning at least one, which would be very complicated. Deanna's school bus arrives at 6, so F means she took the bus. No, F means she made it to class on time. B means she took the bus. So B prime there means she didn't take the bus. Her dad drove her. And F prime means she did not get to school on time. So given Deanna makes her first class on time, so we're talking about on time is this branch and this branch. So you would multiply 0.8 times 0.99, whatever that is, and you'd multiply 0.2 times 0.8, whatever that is. Add those two numbers up. So you're going to add those up. And then you're going to take, let's see, so probably their father drove her to school. So that would be this guy. So whatever this number is in the numerator, and whatever the sum of those two numbers is in the denominator there. And so the answer ends up being, when you do that, the answer is B. Which of the following statements is not true? The two events are mutually exclusive. They are not independent. That's true. If the two events are mutually exclusive, that's the definition of mutually exclusive. The two events cannot happen at the same time. Their probability would be 0. If two events A and B are independent, then that's actually the definition of independence there. Certainly not all 4 are true. It's got to be this one. Two events are independent. They must be mutually exclusive. They can't be, actually. You can't be the same. So mutually exclusive means that one happened, the other one can't happen. So they would have to depend on each other, which independent events don't. Sorry. Okay, so what's the probability of driving an SUV? So it looks like there are 39 SUV drivers. So it'd be 39 out of 120. This one was pretty basic here, or 0.325 when you type it in your calculator. So sedan would be 45 out of 120. The truck, there doesn't seem to be any overlap there, would be 36 out of 120. And so you're just going to add those up to get 81 out of 120. Simplify that. I think that does simplify 27 out of 40, or 0.675, I believe. Was probably the person selected gets a truck or exercises 4 or more times per week. So truck would be 36. So to get that number, I'm adding those two numbers. So 12 in the numerator is 12 plus 24. That's the truck. Plus, to get the exercise, you're adding those three numbers. So 25 plus 15 plus 12 minus the overlap. I think you counted that 12 twice. So that's the numerator. The denominator, I believe, would be the 120. And if you do that, you get 76 out of 120, which simplifies to be 19 over 30, which is about 0.633. This one looks not too bad here. So what's the sample space? So 2 yellow faces, 2 red faces, 2 green faces. So what are all the possibilities there? So you could get, she's tossing a coin, so you get head and yellow, head and red, head and green. You could get tails and yellow, tails and red, tails and green. I think that is the sample space. There are 6 possible outcomes. Find the probability of tossing a tail. Well, tail is just 1 out of 2, right? There's three cases there. Find the probability of rolling, and they're all equally likely, I believe, all those cases. It's good to know. That's not always true. C, yellow or red. So yellow, there's 2 of them with yellow, 2 with red, so 4 out of 6 or 2/3. It's nice when you have the sample space and they're all equally likely. D, heads or green. So let's see, heads. Those 3 are heads. Green is that guy. So it looks like 2/3 as well. So 4 out of 6 are 2/3. So just using the sample space, because they're all equally likely, you can just kind of use it and not have to think too much about those. This is probably best done, I don't think I put in the answer key, but it's probably best done with a tree diagram. Receives parts from 2 suppliers. 40% of parts come from supplier A, 60% from the other one. So let's just, so A and B. So 40% from A, so it must be 60% for this one. 5% of parts from A are defective, so defective, I guess good, like they working. So defective are 5%, so 0.05. So working parts must be 0.95. Defective, this one, and working or good parts. So the second one, 3% are defective from that one, so 97 must be working. Find the probability the randomly selected part is from supplier A, given that the part is defective. So first, let's figure out the defective. So you would get your calculator out and start working this. So 0.4 times 0.05, that's the first defective there, 0.02. Second defective is 0.6, oops, 0.6 times 0.03 is 0.018. If you add up those 2 numbers, you get 0.038, 0.038. Okay, so then find the probability that the random part, I need to read the question, is from supplier A, given that it's defective. So there are 0.038 defective, but we want the ones that are from, so this would be 0.02 divided by 0.038, whatever that is. So 0.526 would be your answer, 52.6. So on this one, in manufacturing of glassware, 12% have a factory defect. A new manufacturing process is introduced with the goal of reducing the proportion of defective glasses. After using the new process, 50 glasses were randomly selected and inspected. In the sample, there were only 3 glasses were defective. We want to carry out a simulation to estimate the probability that no more than 3 defective glasses in a random sample of 50, if the true proportion of defective glasses was still 12%. So there's a dot plot of the simulation. Refer to that as the simulation here. You want to use that in your question. Some of you are saying the graph, but we're talking about this is the simulation, the 100 simulations here, 100 trials. Okay, so how many trials resulted in no more than 3? So if you count all of these, I believe you get 17 dots. So 17 out of 100 were no more than 3. So in the simulation, only 17% of the trials resulted in 3 or less defective glasses. And so it would be the 17%. You want to say that in a sentence there, but 17%. Is there convincing evidence? Some of you are using the word statistically significant. In this case, with a simulation, you don't have to use those words as much as you're just going to talk about it. Is it unusual? Is it not unusual? So how unusual is that? Well, 17% of the time in the simulation, this just happened just by chance, right? Given that there is 12% defective. So this is not unusual. So we don't have enough evidence to say that this is an unusual result of any kind. So we don't think that the new manufacturing process has reduced the proportion of defective glasses. So there's not convincing evidence because 17% of the time this happened in the simulation. So not that unusual. Probably looking for less than 5% or even 0% would be even better for that.